All right, here we have lesson 11, which we are going to do some more practice with Gibbs. So, in the previous lesson, we got our introduction to Gibbs free energy and the change delta G. And the big thing we wanted to know was when will a reaction be spontaneous and when will it be not spontaneous? So we learned about if delta G was less than zero, then it was spontaneous, and if it was greater than zero, then it would be not spontaneous. So this chart below will help you predict under which conditions a reaction will be spontaneous. Now, the thing to remember is this table is just a reference, and it is impossible to memorize this table. Okay, so it's not something I want you to do. What I do want you to pay attention to, though, is the column with delta G. Okay, and the fact that temperature plays a very big role in determining whether the entropy will have an effect or not. Okay, there's going to be a table later on one of the later slides that also has a summary that might be helpful to you. Okay, so again, do not memorize this table. It's not going to be worth your time, but pay attention to how the temperature changes the delta G equation. Okay, and that will help you figure out if our reaction is spontaneous or not. So we can use the delta G equation, right? Delta H minus T delta S as one method to calculate the change in Gibbs free energy. But at 298 Kelvin, we can also calculate delta G by using the Gibbs free energy of formation values in the same way that we can calculate delta H from the delta H of formation values. So, just like entropy, just like enthalpy, we're going to use the sum of the products minus the sum of the reactants using our Gibbs free energy of formation values. One thing to note is that the delta G values are very subject to temperature changes. Therefore, the actual delta G may be very different from the delta G calculated at 298 Kelvin and 1 ATM. Hey, in the data booklet, the values given are at 298 Kelvin, and you most likely would be asked at that temperature to use the enthalpy of formation values, but if it was a different temperature, you might have to use the other equation, right? Delta G equals negative 8, delta H minus T delta S. So let's do an example. Okay, we're going to calculate delta G for the reaction from the following data. Now, one thing to note is we have 4 substances in our reaction equation, but we're only giving the data for 2 values. Okay, the iron 3 oxide and the aluminum oxide. We are not given the values for aluminum and iron, and that is because they are elements. So just like enthalpy of formation had a value of 0, Gibbs free energy of formation also has a value of 0. So first we're going to write down our chemical equation with the values that we are given. We note that they are, they need to be included with the coefficients if there are any. And we would do sum of the products minus sum of the reactants. And we will see that delta G equals negative 840 kilojoules per mole. And because it is negative, this reaction is spontaneous under standard conditions. Okay, here's another example. calculate delta G at 288 Kelvin for the thermal decomposition of calcium carbonate from the following data. Okay, so we are given all of our compounds, and we are given the enthalpy of formation values as well as the entropy values. And we're going to calculate delta G at 298 Kelvin. Okay, so we're not given the Gibbs free energy of formation values, so we're not going to do products minus reactants using those, but we are going to use the delta G equals delta H minus T delta S. But the first thing we have to do is we have to calculate delta H. Okay, we have to calculate the change in enthalpy. So from our equation, which is the thermal decomposition, which you could see on the slide there, we are given the enthalpy of formation. So when you see enthalpy of formation, you have to do sum of the products minus sum of the reactants, taking into account any coefficients. In this case, they're all 1, so that's not going to play a role here. So you do products minus reactants, and you get an enthalpy change of 178 kilojoules per mole. Okay, so that's our first step down. The second thing we have to do is we have to calculate the change in entropy, okay, delta S. We're going to do the same thing. We're going to do sum of the products minus sum of the reactants, given the values in the table. Okay, so do products minus reactants, and we get 160.8 joules per Kelvin per mole. Okay, so again, we note that the units for delta H and delta S are different, and that's going to play a role in our third step when we're going to use the Gibbs free energy equation. So we would do delta H minus T delta S, and it's noted that the units are different, so one of them must be converted to the other. Since delta G is given in kilojoules per mole, it is easier to just change the delta S to kilojoules since it's just in joules, so all you have to do is divide by 1,000, which is noted in the problem here. So do delta H minus T delta S. Our temperature is 298, so that is where you see there. We divided the 160.8 divided by 1,000. That's why it's times 10 to the negative third. And when you do that, you get delta G is positive 130 kilojoules per mole. So the thermal decomposition of calcium carbonate is not spontaneous at this temperature, 298, because our delta G is positive. Okay, so you have to pay attention to what is given in the problem to figure out, are you going to use the Gibbs free energy equation like we did here, or are you going to do the Gibbs free energy of formation values? Okay, let's do a couple of practice questions. Number 68 says the enthalpy and entropy changes for the reaction given below are delta H equals 100, delta S equals 100, and we have to figure out is the reaction spontaneous or not, and what kind of role does the temperature play. Okay, so let's take a look. All right, so we know delta G equals delta H minus T delta S. Okay, so that's our Gibbs free energy equation. All right, we know that delta H is 100. And then we're going to keep T for now, and we're going to change 100 to 0.1. I'm going to divide it by 1,000. So that way it's automatically in kilojoules. Okay? So remember, if delta G is less than 0, it's spontaneous, and if it's greater than 0, then it's not spontaneous. So if we set delta G equal to 0, we can then solve this equation. Okay, so 0 equals 100 minus 0.100t. We can bring this to the other side, and that gets us 0.100t equals 100. And I can solve for t by dividing by 1,000, or dividing by 0.1 to get t equals 1,000. Okay, so by setting the delta G equal to 0, we can look at the change that temperature will have on the spontaneity. Okay, so the 1,000 is the number. Okay, so let's just go through our questions. Okay, letter A says the reaction is not spontaneous at any temperature. Okay, well, not spontaneous would give us a positive value. But if temperature is really, really high, then this T delta S right here is going to be really large. And when we do 100 minus a really large number, that's going to be negative, which is spontaneous. So A is out. The reaction is spontaneous at all temperatures. Okay, well, we said if temperature was high, then delta G is going to be negative. But what if the temperature was low? If it was like 0 or a really small number, then when you do 100 minus a really small number, delta H is still going to be positive. So delta G is going to be positive, which would be not spontaneous. B is out. Okay. We calculated the temperature where there's going to be a change in the spontaneity. So now one thing we have to consider is the Celsius or Kelvin. Well, the temperature that we use in this problem must be Kelvin. So that means our answer is letter D. At above 1,000 degrees, when I put this 1,000 into this equation here, this second part is going to be really, really large, and it's going to do 100 minus a really large number, which is going to give us a negative value. Okay, let's try number 69. Magnesium carbonate, MgCO3, is a white solid that occurs in nature as the mineral magnesite. Magnesite decomposes to the oxide at temperatures above 540 degrees Celsius. Okay, so we have the equation for the decomposition. Identify the correct description of this reaction at 800 degrees Celsius. Okay, well, it says here it decomposes at temperatures above 540. Well, this reaction is occurring at 800, right, which is above that 540. So for a decomposition, one of the things to note is you must add energy for something to decompose because you have to break those bonds. Well, if you have to break those bonds and you have to add energy, that means delta H has to be positive. Okay, well, if we look at our options, the only one that doesn't have delta H as positive is B, so I'm going to cross that out. Okay, we can also look at our equation and consider our change in entropy. We're starting with something that is solid, and we're ending up by making a gas. So because we're going from something that is ordered to something that is more disordered, our entropy is also increasing. So we have a positive change in entropy. So that eliminates letter D. And now we want to consider our delta G. And then this is where the temperature is going to play a role. So this, it says it decomposes at temperatures above 540, and our reaction is going to occur at 800. So since it'll occur above 540 and our temperature is indeed above 540, delta G is going to react spontaneously, which means we have a negative delta G, which means A is out, and our answer is letter C. Okay, so just by looking at the reaction, the equation, I figured out my delta H and my delta S, and then I took the temperature and figured out my delta G. All right, 70, calculate delta G for the thermal decomposition of calcium carbonate. Okay, we did before this exact same problem, but we were using the delta H and the delta S values. Here we're given the Gibbs free energy of formation values, which means you have to do products minus reactants. And when you do that, you would get positive 131 kilojoules per mole. Now, as you can see here, this value is very positive, and it is not spontaneous under standard conditions. Now, calcium carbonate, if you did not know, is a primary component of things like limestone, chalk, and marble. And those substances are quite stable because it will not decompose under these standard conditions, right, as we just calculated. All right, number 71, we want to calculate delta G at 2000 Kelvin for the thermal decomposition of calcium carbonate from the data given in the worked example. So the worked example in this problem is asking specifically about the one where you're given the delta H and the delta S values. Okay, so you can check your notes. But you are given the delta H as 178. That's kilojoules per mole. And we're given the delta S values as positive 160 joules per Kelvin per mole. Okay, and this time we're given 2000 Kelvin. So before it was at 298 Kelvin, I believe. But now we're going to really raise the temperature up, and we're going to use 2000. So you have to input the Gibbs free energy equation using 2000 instead. And when you do that, you should get a value of negative 144 kilojoules per mole. So previously, under standard conditions, that value was positive, meaning it was not spontaneous. But as soon as we raise that temperature really high, we now have a very spontaneous reaction, negative 144 kilojoules per mole. Number 72, which property of an element has a value of 0 in its standard state? Okay, so we mentioned that 0, okay, which one have zeros when elements are in their standard state? Okay, well, we talked before about enthalpy of formation. That was a definite yes. Entropy was different. Every element has its own value. So that's a no for entropy. And then we just introduced our Gibbs free energy of formation, which is very similar to enthalpy of formation. So those elements have a value of 0 in their standard state, giving us 1 and 3 as true. So our answer is letter B. Okay, number 73 is a good example of a problem that you could see in an open-ended question where you have multiple parts and you have to use the values that you get to answer the next part. So the standard enthalpy change for the formation of ethanol and its molar entropy are given in section 12 of the data booklet. So if you haven't realized by now, section 12 of the data booklet has values for entropy, enthalpy, Gibbs free energy, I believe. So this is going to be a really useful section when you're doing these kind of problems. Letter A says write an equation for the formation of ethanol. Okay, so you want to form ethanol, specifically 1 mole of ethanol from the elements in their standard state. So we need to include carbon, hydrogen, and oxygen to get our C2H5OH. And that's what we see there. Okay, carbon is graphite in standard state, hydrogen is diatomic, and it's a gas, and oxygen is also a diatomic gas. Okay, the coefficients must equal what we have for the number of atoms for each element on the right-hand side. In letter B, it's asking to calculate the entropy change for this process. So the entropies of its constituent elements are given there. So in order to calculate the entropy change, we're going to do sum of the products minus sum of the reactants. So we're given the equation, we're given our values. When you plug those in, you do have to take into account the coefficients. So you need to take 2 times the 5.7 for carbon, 3 times the 65.3 for hydrogen, and 1/2 times 102.5. Now the 161 for ethanol comes from the data booklet, so you should find that there. That is our product. So when you do this, you get an entropy change of negative 98. Okay? Now one thing to consider is, does that number make sense? Well, we're going from gaseous reactants, in the case of hydrogen and oxygen, to a liquid, which is more ordered, a more liquid product. So it would make sense that our entropy change is negative, it decreased. In letter C, it's asking to calculate the standard free energy change of formation of ethanol at 500 Kelvin. Okay, so for letter C, since it's asking for standard free energy change, we have to find delta G. And we need delta H and T and delta S. We're given the T, which is 500. We just calculated delta S as the negative 98 joules per Kelvin per mole. We just need the delta H. And since no values are given to us for this part, we must look in the data booklet. And what we will see is the enthalpy change for ethanol is negative 278. And then we're going to input our 500 for our temperature, right? So we have delta H there minus T delta S. So we divided the 98 by 1,000, so it's in units of kilojoules. And when we do that, we would get a delta G as negative 229 kilojoules per mole. In letter D, it says deduce whether the reaction is spontaneous at 500 Kelvin and give a reason. This is a common question where you would calculate the value for delta G in one part and then ask about the spontaneity and give a reason. Well, if we look, delta G is negative 229. So we would say that the reaction is spontaneous because delta G is negative. And finally, in letter E, it says predict the effect, if any, of an increase in temperature on the spontaneity of this reaction. Okay, so let's say we increase the temperature, make it really, really high. Okay, well, when the temperature is really high, the enthalpy change does not matter. It is not significant. So delta G is equal or approximately equal to negative T delta S. Okay? Well, we know that delta S is negative. So if we were to do a negative delta S times the temperature times the negative at the beginning, you would get a positive number, and therefore the reaction will stop being spontaneous at higher temperatures. So to sum up delta G, a negative delta G means that a reaction can happen without additional work being put into the system, but it does not mean it will happen, and it also does not mean it can happen fast. Okay, so just because a reaction is spontaneous doesn't mean that it will happen. Okay, and if it does happen, it could actually be a really, really slow reaction. And the speed of the reactions is something that we're going to learn when we do kinetics. A really common example is diamonds. So carbon, right, we know can be converted into diamond, but it is a really, really slow process that really only occurs under the conditions of high temperature and pressure. So it can happen, but it's a really slow process. So another way that we're going to see Gibbs is in our equilibrium, which is unit 7 and 17. We'll talk about what equilibrium is, but Gibbs free energy is related to equilibrium. We know that not all reactions go from all reactants to all products. Many reactions reach an equilibrium where we have both products and reactants in a mixture. So equilibrium is when the rate of the forward reaction equals the rate of the backwards reaction and the concentration of reactants and products stays constant. When we look at equilibrium, we look at the ratio of the concentration of product to reactant. So we would divide the two concentrations. So where does delta G come in? Okay, how does it play a role? Well, we know that a reaction is spontaneous with a negative delta G. But as delta G becomes more negative, the reaction is more spontaneous and will favor products to reactants. We can then say that if delta G is below approximately negative 30, the reaction typically goes to completion and all reactants becomes products. But for example, if delta G is between negative 30 and 0, there is an equilibrium formed, and that means we would have both products and reactants. Here's a table that kind of sums up how Gibbs free energy and equilibrium are related. So I'm actually going to start at the bottom where we just had the delta G was much smaller than negative 30. that means we had a complete reaction and all of our reactants turned to products. If it was between 0 and negative 30, it's a partial reaction producing an equilibrium mixture. If delta G was equal to 0, we also have that partial reaction producing an equilibrium mixture. We have about an equal amount of products and reactants. If delta G is between 0 and positive 30, we have, again, a partial reaction, but we have mostly reactants. And if delta G was much greater than 30, we would have no reaction because it would be not spontaneous. Okay, let's do a couple of practice questions just to wrap up this little look at equilibrium. So, number 74, what signs of delta H and delta S for a reaction result in a complete reaction at all temperatures? Okay, so if we were to do delta G equals delta H minus T delta S. All right, so it says a complete reaction, which means it's going to be spontaneous at all temperatures. Okay, so that means delta G has to be negative. Okay, so in order for delta G to be negative at all temperatures, okay, the first thing that plays a role is delta H. Okay, well, if we want delta G to be negative, we also want delta H to be negative. Okay, we want an exothermic reaction, so we want delta H to be negative. So if we look at our options, B and D are out. Okay, for all temperatures, we want an exothermic reaction. But now we have delta S, so we want our delta G value to be negative, right? That's our goal. Okay, delta H is negative. We figured that out. Okay. The temperature plays a role, right? The higher the temperature, this is going to overpower it. The lower the temperature, delta H is going to overpower the equation. So what we want is to ensure that this value is going to be negative. We want to subtract a positive value so that way we keep delta G as negative. So we want delta H, or delta S, to always be positive. That way we're always subtracting a positive number. So if delta S is positive, A is out, and that means C is our answer. All right, number 75 is kind of a tricky question, so I'm just going to give you the answer for now. But this question will make more sense when we talk about equilibrium. Number 76, which values correspond to a reaction that can be reversed by changing the temperature? Okay, which values correspond to a reaction that can be reversed? Okay, reversed meaning the equilibrium going forward versus backwards, making more products versus making more reactants. Okay, well, going back to that delta G equals delta H minus T delta S, okay, if we change the temperature, that is going to affect the second part of the equation, where the T delta S is going to be more significant or less significant based on what the temperature is. Okay, in this case, both options 1 and 3 are going to allow you to reverse the sign of the delta G. Okay, here's a nice little table that shows a summary of Gibbs free energy using delta H and delta S values and how temperature affects. Okay, so it's very similar to the table that I introduced at the beginning, but it is, I think, a little more simple to see if delta H is positive or negative, if delta S is positive or negative, and how, in fact, the temperature does play a role. And we can see that the previous question that we just answered is given in the last two rows, where delta G is positive at one temperature, but negative at a different temperature. Okay, so this would be a nice little table to use as a reference as well. But again, try not to memorize the table because it's going to be tough. All right, we have two more questions. They are very, very similar. So I'm just going to do 77 and then I'll show you the answer for 78 because it's pretty much the exact same thing. So in 77, it says propene reacts with hydrogen in the presence of a nickel catalyst to form propane. Okay, so we're given the equation. We are given delta H and delta S for the reaction. And we want to estimate the temperature range in which a mixture of all three gases will be present. Okay, so we know that if delta G is less than negative 30, we're going to have mostly products, or all products, excuse me. If delta G is greater than 30, then we're going to have only reactants. So what we have to do is calculate delta G, or excuse me, use those values for delta G and calculate the temperature at each value. So if we use delta G as negative 30 and input our equation and solve for T, we get a value of 727 Kelvin. Now when delta G is positive 30, we get a temperature of 1195. So what this means is any temperature between 727 and 1195 Kelvin would give us an equilibrium mixture. We would have all three of these gases. Like I previously said, if it was less than negative 30 and the temperature was lower, then we would only have products. If the temperature was higher than 1195 and the delta G was greater than positive 30, we would only have our reactants. Now 78 is the same thing. You can try it on your own before you put up the answer, and you will see that for this reaction, the temperatures are different, and that's because the delta S and delta H values are different as well.